very last part of the talk. There was at a certain point a recognition that the fragmentation and evolution of the asteroids could proceed in a different way. So basically, other researchers in the area proposed what is called the pancake, what has been called later, pancake approach. So basically, the Chiba and co-workers, what they did was actually to consider no more the asteroid as a sphere, but as a cylinder, as a cubic cylinder, so where the diameter and the height of the cylinder are equal. And using some of the hydrodynamic approximations, what they did was to develop a very approximated and simplified approach to consider the actually the change of shape of this cylinder, of the cometary cylinder, the meteoroid cylinder, a change of shape, and in particular the fact that as a liquid or a simplified liquid, this cylinder under the pressure or under the flow pressure, the airflow pressure, would actually become more flatter. So the evolution from this configuration to the other configuration, bigger radius and smaller height. And the approximation basically is the small simplified equations that they derived is these equations that gives the evolution in time of the radius as a function of the characteristics of the density and the drag, basically. Simply so, this is why it is called pancake, because what simulates is actually the deformation of the body to a pancake, so a very flat cylinder. It can be used in some to describe some of the phenomena that were recorded in history, and one of the things is if you do not put any limit on the maximum radius, the model, if there is enough time up to the ground, the model will predict the change in radius up to infinity. So the numerical implementation of this model basically brought to the fact that for real applications there should be in the numerical model a limit, an artificial limit, which again should come from available data. And so it is at that time. This is information from a paper in the 2009. In order to have a good simulation, the flattering factor, so the ratio between the radius and the height, should be around 2. There are things that there are some instabilities that occur. Of course, what you have, so that there are instabilities. Probably some of you know much better than me. That basically are instabilities that happen when there is two different fluids with different densities which are interacting each other. So Rayleigh-Taylor, the Rayleigh-Taylor instability is the instability that probably will make impossible to create fusion by plasma or laser containment. And the pancake model in itself cannot actually, both of the models cannot actually explain totally all the experimental, all the evidences that we have. So basically, as it happened, because due to the fact that the models actually are some sort of asymptotic model, the reality is in the middle. So what we have is a mixture of pancake formation and some of the fragments that actually travel on the ion. And basically, what some of, again, Artemieva and colleagues did was basically to model, to create a numerical model which takes into account both the approaches and can reproduce the pancake model also with small modifications to the separate fragment approach. So, as I said, all these models are used to have some bounds, to have some preliminary knowledge about the speed and characteristics of the fragment. But then the idea is that once there is a clearer idea of the composition and the structure of the asteroid, some more high fidelity model could and should be used. So, for example, Shuvalov, well, there is a lot of literature on this SOVA hydrocode, and which basically can, if the user inputs the correct data, can basically model all the phenomena and all the asteroids that can actually be simulated, all the asteroids that can be simulated as a strengthless liquid material. So, few words on submuon developments. As I anticipated before, now there is, like people in Stardust, there is a cross-contamination. Some of from the aerospace field are working also on the asteroids. And there are new things. For example, Lawrence and co-workers in 2012 published some new results, both experimental and numerical results, on the correct value of on the correct modelization of the transverse velocity for the fragmentation approach. And basically what they found was that the model from the 80s, which was actually improved and verified by the hydrocode, was not totally correct. Probably because both the authors actually assumed that there was a purely lateral separation, but also other people, for example, people that used the hydrocode, do not properly simulate, do not properly simulate the interaction between the bodies and the shock wave. And this confirms basically that the shock wave is one of the most difficult and important things to consider to properly simulate entering phenomena. So basically what happens in reality, and what was experimentally and numerically found, is that the secondary body, if it is smaller than the primary one, actually is surfing, is not basically just pushed away from the primary model, but it is surfing the boundary, the shock wave, and it is moving also axially. And that gives different, so they used They proved that experimentally. So this is an experiment, one of the experiments in one hypersonic cannon. So as you can see here, there are at time 0 a main body and a secondary one. So the secondary one in this case is very small compared to the primary one. What happens is that the small body basically is do not develop its own shockwave, and basically is just traveling axially and not transversally. When the radius of the two bodies is the same, what is confirmed is the previous law from the 80s. When the radius is small but not really small, what happens is that it travels transversally and also axially. So since the pictures are taken at the same time, more or less, you can see that when basically the secondary body is surfing this shock wave, it is pushed away much at higher speed. So basically what happens is that if the dashed curve here represent in this graph the adimensional transversal velocity given by the previous Passey and Melosh law, this is what actually happened in reality. So C cannot be considered constant. That parameter cannot be considered constant, and actually it depends on the ratio between the radiuses in the radiuses of the bodies. And they performed this at they performed experiments at one single Mach number, and they confirmed the experiments by numerical analysis, CFD in this case, no hydrocode. And then what they did was actually to use the numerical approach to see what is the effect of the Mach number on this. So basically there is the same kind of behavior, but the maxima are different and the position of the maxima are different in terms of the ratio between the radiuses. So this is something new happening. So still the idea is to use in this case the approximate model, simplified model, because it is easy for preliminary simulations. But if we want to have more realistic results, then we need to account for these changes, and for the fact that the C is not constant. And basically, it is what we hope to do. Some kind of contribution for Stardust in this area could be actually to new models or new insight in this phenomena, due to the fact that we have different technologies, different tools, and so different simulations can be done to prove how we move. And basically, this is all a little bit earlier, but not much.
Thank you very much. Some questions? We have time. Yes.
In the model that you showed with the two bodies moving transversely, do they carry spin energy away? Are they spinning while they go off, or are they just moving?
It is not mentioned, so probably they are not spinning.
Okay, because I'm assuming in reality there's spin induced as well. Are they fragmented?
But in reality, they will not be spheres. They will be different shapes. So yes, there will be other things. Yeah.
Okay, so I was just wondering if you have any idea of how far then this is from or which factors, like spin or anything else, would be the most important to add to?
Well, I don't think that spinning could give something something really important on the top of this big change. This is already something. What they also studied was the position, the initial position of the fragment, let's say. So, for example, here the fragment is immediately at the top, but they also consider the fact that you never know where it is, and so another parameter for which I didn't show any result was to consider different thetas, so different positions compared to the main body. But the general behavior is the same. So the values and the position in ratio of the radiuses is different.
Do you happen to know what is the velocity and the pressure, the atmospheric pressure for that picture? Yeah,
there is everything in the paper. I can give you the thing. But the fact is that this is for very low ultrasonic number, so it is 4. But they say that they are confident that this is the same behavior that happens to very high hypersonic. But the paper is quite well detailed, but I think it
Are there any simulation tools that can produce, because until now we have just seen the breakup of asteroid and then the fallout to the ground of the pieces. But what happened in Chelyabinsk was the explosion.
Yeah. Sorry, I totally forgot to say that. That basically what can be used to model is well, Chelyabinsk and all the others are phenomena that occur when there is some sort of pancake phenomenon. So it is the pancake that at a certain point becomes so fast that it is like an explosion. So they actually simulated Tunguska and with the pancake model.
Any other question? I have a naive question. No, in a sense, in the artificial re-entry, concerning the behavior and the location of the re-entry.
Yep.
In the artificial object re-entry, we know that they are very dependent on the status of the atmosphere in the last orbits of the re-entry. In the asteroids, given the angle of the trajectory, given the velocity, is there any influence of the status of the atmosphere?
Due to the fact that there are very, very high energies compared to the...
Doesn't count anything. Just a flat.
Yeah. Well, the density of the atmosphere is taken into account in the models for the fragmentation and the things, but at the end,
the
variation cannot be such that there are changes.
So I just would like to come to the question before. You said a pancake is used for, let's say, a Tunguska type phenomena, while you're talking about this correlation of this semi-empirical model with crater. But crater formation process, as was pointed out, is not only the number of individual fragments that impact, but is really the physics of impact.
Of course.
And we know that, for instance, I seem to remember that impact with, let's say, spherical objects in planetology with a grazing impact. There is this fact that the impacting sphere has a shear stress and separating two. So there's also a formation of the crater that depends on not only on the history during the atmospheric re-entry, but the real impact phenomenon.
Of course, yes, but this is another. This is some sort of post-processing. The tools are from the entry. These models are from the entry to the vast of the fragmentation to the ground. then there is another site or another field that
So
causes
the
that
thinking for the
impact.
crater needed another step.
Yeah, another step. Yes.
Claudio.
How about the use of real data like TV re-entry to check these models?
Yeah, they are done. They are semi-empirical models, but at the end there is so uncertainty also in the data which is available, a big number of assumptions, and it is very difficult because all the data do not have all the answers.
But is anything being done to improve this in the future, to put some sensors or to some cameras? Or
Not
the
really.
ATV during the...
Yes, I don't remember the name of this stuff that was built by Aerospace Corporation. It is a sensor that is also probably would be is flying on the last ATV here. It has been also it's just an object that is inside, and during their re-entry at a given point is released and transmits data through Iridium or at a GPS and transmit the data inside, and that will be used to correlate re-entry stuff. But I don't remember the details.
Well, I can add to that maybe. I was involved in an airplane campaign to observe the re-entry of the first ATV. So we had 2 airplanes flying and we observed the re-entry. Okay, I have some cameras where I normally observe meteors, and we used that, and there was a big team with Americans and everything. Of course, we enjoyed that very much, and we said for the second campaign we need to do that again. And what the people, our colleagues in the Human Spaceflight Directorate told us, they modeled and compared what we observed with Scarab. And they were so happy how well Scarab performs that we will not get funding for a second campaign anymore. It's not needed. Okay? Now, having said that, what you mentioned is right. For some reason now, for the last re-entry campaign, I was approached half a year ago or something. They wanted to do another observing campaign, and there's a company in Stuttgart who has a contract to do this again. So maybe some people got doubts, and they definitely added this little sensor type thing, which transmits data then from the re-entry. But that I didn't follow anymore because they didn't pay me. So So, okay. But the Scarab test was done compared to ATV, and the initial conclusion was it works extremely well.
Marco.
That was
Yeah,
the
after
question
those,
answered.
okay.
It was tested, so...
Okay. Okay, if there are no other questions, thank you very much for your